Hello? It's audible, right? Okay.
So, our project topic is permutation matrix, and our team is here, and I'm Rajnigal Sema. He's Rishikesh, and he's Ankumar Gupta. So, my paper is about average case column subset selection for entry-wise L1 norms loss, and, and it is from NeurIPS conference. So, coming to what is average case CSS. So, what we do here is instead of working on the worst case input, we are working on we are assuming a matrix with A star is the low rank matrix, target matrix with true values, and delta is the noise matrix with IID entries. With the ID entries of finite distribution, finite moment distribution. So, what are the applications of it? Like it can be used in robust machine learning, computer vision, and fair and structured learning, etc. And talking about low rank approximation, it is needed for dimensional reduction. Like what we are doing here is selecting some columns out of A matrix and then using it for reconstructing the another matrix B. So we are doing here dimensionality reduction and reducing the noise depending on the column's weightage. So it improves its efficiency while generating B matrix. So what is low rank approximation? I have already discussed it. Like it is a matrix given a matrix R on R n cross n matrix. We need to find at most k columns, rank k columns with from which we can form a matrix B while minimizing the error, absolute error A minus B. So it is also used in PCA, like where that we uses we minimizes a Frobenius norm, Frobenius norm which is also a L2 norm. So where that we do squared minimizing squared errors. So in L1 norm we minimizes the absolute errors unlike L2. So it is NP hard to optimize because it is we need to consider outliers as well. So what are the key contributions of this paper? It runs effectively while achieving a time complexity of O order of n square plus n poly KL log n so epsilon. It outputs are using the it outputs using L1 regression. So here it is a noise model where A, I already explained that A is the matrix and A star is a is a matrix with true values and delta is the noise. Uh, so uh, finally, what we are achieving here is using L1 norm. We are achieving a approximation of 1 plus epsilon. So what is the problem? A problem it was to minimize the error between the matrix A and matrix B. So we are summing up to all columns and rows. So on this prior works has been done with the approximation of order of k log k, and here we achieved order of 1 plus epsilon. So what was our existing L1 approach? Existing L1 approach we achieved a runtime of n poly lk, which is impractical kind of. So we can't go with that. So and also in Frobenius method, optimal solution with SVD also done. For that example was single corrupted entry where outliers extended the error to a large extent. So I explained it already. And what is permutation connection here? Like we are using k columns for informative columns constructing a B matrix, and we are considering noise dominated columns to discard them. Like where noise is large, we are discarding them and instead choosing the one columns which have low noise. So here is our algorithm one, where what we are doing, like we have to randomly select columns and then checking its error through checking minimizing its error with the matrix and detecting outliers where the residual error is higher, and when then finding the best columns. We are refitting the columns to construct a B matrix. Uh, using that, we are achieving 1 plus epsilon approximation.
But this is a randomization algorithm, right?
Yeah, no. First, we are randomly picking up columns and then minimizing their errors based on its noise.
So you just the set of random columns is fixed, is it? Or is it? Do you have multiple random set selections or just once?
Multiple.
So sample a set I. Step number 2. Sample a set I from and choose an uniformly at random, whereas it's polynomial and k y epsilon. Fine. But then where are you choosing that? It's happening only once. It's not happening multiple times, right?
We are iterating it back to back because we need to select more columns which where the noise is less. So optimally, we are getting some columns. Using them, we are constructing B matrix.
I'm not understanding. This seems to be happening only once. You're saying it's happening again and again. You randomly select I only once, right? Where is it written that it's solved again and again?
Sorry, I think I misinterpreted as single columns. It is for S columns.
No, it's select S columns. Fine, it's
Yeah.
selecting S only once, right?
Yeah, S columns.
So this is basically a randomization algorithm. Now, the analysis, I mean, output is A I union Q with 1 upon 1 plus epsilon approximation, despite being random. One plus epsilon. What is epsilon? Hmm. What is that? What is epsilon?
Uh,
Oh, that's an input. Li noisy low rank approx as an input as epsilon. What is 25? Reference 25?
reference 25 is given for the output generating B matrix. Like we have collected Q matrix, completing formation of the matrix B. Like weighted columns which have higher connectivity with the higher reference, higher relevance. It is given in a research paper. There's a reference 25.
Okay, but I would still like clarity on whether this is just a randomization
Like
algorithm.
we
You just
can do it. Yeah, it is calculating the error and minimizing it. So here algorithm 2 is here. What is the basic difference between algorithm 1 and 2 is where in algorithm 1 we are minimizing the mean, and here we are minimizing the median for the matrix. So this is the basic difference. Like in algorithm 1, which is theoretical, we use theoretically, we are achieving 1 plus epsilon approximation, and in algorithm 2, which is a robust heuristic. And what is doing an algorithm 1, we are averaging, and in algorithm 2, we are finding median to find the best possible columns. So coming to its use cases, algorithm 1 is basically uses in theoretical guarantees where there are not much outliers are there, and in algorithm 2 we are more towards real world data where outliers are maybe present. Yeah, in averaging we are considering all the errors and minimizing it, and in median we are considering the major major errors which are coming at median, because their outliers may be present, and if we are considering outliers, the errors may be enormously high. Yeah.
Can you just show again algorithm 2? What exactly is algorithm 2 is still not clear. So in algorithm 2 for matrix A, target rank A, blah blah blah, it's still randomly selecting S columns. For each column, I compute median regression. So it's a median regression. Keep columns with smallest median residuals. That's the only difference. So step 4 is basically the difference. Columns with smallest median residuals.
where X is the, sorry, yeah, it is noisy. Yeah, yeah, yes.
So can we say that algorithm 2, algorithm 1 was more from a theoretical
Yeah.
interest? Algorithm 2 is the one practical, but it's also inspired by algorithm.
Yeah, but it is basically for the mainly for the real world data.
This is how we can write papers, right? I mean, in many cases, you not able to identify very generic conditions under which theoretical guarantees can be provided. So restrict the scope and then get that. I mean, that's what happened in practice also. Adam and all got very much inspired by all this acceleration method. Not that every new algorithm will do guarantees, and especially non-convex settings. Okay, go ahead.
So here is our experimental setup where we have compared algorithms. Like it was given in the research paper. It is not mainly completely given like how we are using these other three algorithms. It is given about the median heuristic, which is our algorithm 2, and we are using data where we have synthetic data of 500 plus 500 uniform entries and the real world data from isolate and mfit. So there's a large data for real world data, and there are two noise models where Levy 1.1 stable is there and a modified Cauchy, and where Cauchy Cauchy and Levy have a very high tail data, and modified Cauchy is like where we have Cauchy errors, Cauchy noise, and it's reducing its noise by by its approximate power of 1 upon 1.1. So it is our experimental results where a proposed algorithm 2 is performing better on behalf of on as compared to other method algorithms, where Levy noise is very much less as compared to others, and also in real world data, modified Cauchy is also less. So we can see like median heuristic consistently shows best performance in real and synthetic data as well. So here is our results. Like what paper mainly contributed towards it, like it achieved 1 plus epsilon approximation for low for L1 low rank approximation for mild noise, and achieved a runtime of this order of n square plus n polygon k log, and with a column selection uh, time, which is polygon k epsilon and to order of k log n. So highlights of the experimental one. This is a figure one, and where tested distribution is about Levy noise and modified Cauchy noise, where we used data sets of synthetic and real world data. So that one is a synthetic data, and this is a real world data in lower column. So we can see uh, like approximation ratio is higher in SVD and L1 low rank uh, in the synthetic data, and also in other data as well. So approximation ratio is higher.
Sorry, what did you mean? What is it? Approximation ratio is higher where? I can't see.
Approximation is ratio is higher in SVD and as compared to L1 for lower K value. Like as low as our K, the better the L1 low rank approximation is performing.
And the lower the K,
Yeah.
the better is the improvement we see with the median. You're talking about median or even L1, L1 low rank? What is being plotted here is approximation ratio. Median is pretty poor, is it? Acha, median should is poor. So lower the, yeah, I mean you'd like low approximation.
Sorry.
You'd like low approximation ratio, right?
Yeah. The L1 low is yes lower approximation ratio.
Low, right? But L1 is generally high.
Yes.
So you're saying empirically L1 is not giving good. I'm not understanding.
L1 is comparatively better than SVD. While talking about lower K, like approximation ratio is comparatively lower. So the approximation
For
is
L1 then SVD, but no, I'm seeing SVD is often kind. Acha, for low values of K.
yeah.
For low values of K is what you're saying. K was what again? Sorry, K.
What number of columns?
One low values of K. Yeah. But otherwise, median seems to be in general.
Like that's why we are minimizing for at most K columns, as low as our columns. That because noise will be higher for higher column. So this is a result breakdown. Like synthetic data is top one is synthetic data and real bottom is modified Cauchy real data. So basically is again there's the proposed method yellow that uniform and median. Proposed method is the median. Median is the proposed method which is lower in noisy, lower in noisy Levy noisy and Cauchy noisy, which is around 1.2x and 1.5x error. Wherein other methods, like here we saw, wherein other methods the noise is much higher. So coming on to the conclusion, what was our core problem, which is like L1 low rank approximation was hard because it was NP had optimization, and the existing method was very slow and weakly guarantees because, and also there was not guarantee like it could provide 1 plus epsilon approximation. They were providing approximation around poly of k log n. So and it was also sensitive to heavy tail data where higher outliers they may contribute to higher noise. So what was our breakthrough? And we achieved 1 plus epsilon approximation with the runtime of this and practical robustness of while using algorithm 2 which is better for our real world data, which is performing better because while considering the outliers. So theoretical foundation averaging works as we saw about the median and averaging. Or averaging works under minimal assumptions where we just assume finite pth moment. So first moment does not exist where hardness is more. So that's it for myself.
I see averaging works under minimal assumptions.
Yeah, there was only one assumption that finite pth moment we are considering for the data. Like
What is averaging? I didn't remember.
averaging was yeah, minimum considering the minimum making the error minimized while using algorithm 1 where we are minimizing the error.
Acha, the mean part. Works under minimal assumption.
So what we want, given a matrix, we want to reconstruct it using practically projection of the matrix on a substance. So how it works, it tries to minimize the number of columns and given how we can get the number of columns, the reconstruction here is also. So how we calculate the reconstruction here in the standard process selection loss. So given the matrix n, and we are getting three columns and we are getting projection over n. So just a as a particular in coordinate form, we get it at a loss function and we try to divide it.
So this also decide the quality of our selection of
our section of the problem space. Yeah, so it doesn't perform well overall, like when the data or matrix that we are getting is very homogeneous. If it has a minor group and major group, it has some bias. So it doesn't perform well because it can align with the majority group. The data is not fairly, data reconstruction will not be fair for the both groups. That's the problem. So it introduces a new method called pair problem subset selection. So what does it do? It tries to divide the matrix into two sets in uh, based on its rows. Let's say there are m rows, so we ended m1 rows and m2 rows in separately, such that m1 plus m2 is determine m, the total rows. Yeah. So here the mathematical formulation how we can do that. So what we are trying here also, we are trying to find this problem subset, a common problem subset, so that the whole group reconstruction error gets minimized for both of them, the matrices that we are making. So how we do that? Um, so loss function is created, and A is the first matrix that we are created by taking the subset of rows, and B is the second one. So I have depended for one of them, and similarly we can depend the B for B also. The projection matrix is calculated with the method of pseudo inverse. And what is ATA here? So ATA acts as a baseline or reference where we calculate for best and T approximation, which can also be calculated with contented SVD.
What is sacrosanct about two groups?
Yeah.
So relative group, so I mean, are you comparing across the two groups? Relative group wise reconstruction error. Is it looking at one group with respect to the other?
No, actually, the loss function created for separately for both groups, and then we will see for which the error is coming maximum. That is on the next slide, and we will try to minimize it. That is on the next slide.
I'm still not getting the rationale. Why two groups?
Yeah, that's what I said. There can be bias in the given matrix, such that when we have reconstructed it, it can fair or it can support the majority group. Like the reconstruction may not be fair to the minority group. So what is it is doing? It is separating the given matrix into two groups, A and B. As normally the data is stored such that the different data points are different rows. So it separates it out and makes two groups. Although there can be, it is possible that we can try with different more groups, not only two groups. There might be the possibility, but the research paper deals with only two groups. And it says the further research can be done.
I mean, we are not taking relative of one group. Yeah, I mean, rows of matrix are partitioned into two groups such that A plus B then to find a common column subset C, and C is subset of M. Just that each, so that the column subset can contain some from A and some from B. The column subset C is not a subset of A or subset of B. It can span both A and B, right? Such that each group's reconstruction error is low relative to its own best rank minus K approximation.
Yeah.
So you have relative, so there are A and B, relative group wise reconstruction error of A is only with respect to A. There's no B there. You can have similarly for B. I mean, what is connecting the two? So PCA, PAC, the pseudo inverse is a projection of A onto CA. Again, there's no B. And then AK is the best rank K approximation. Missing. I mean, what is the intuition behind two groups? It's totally missing. Why two? Why not three? Why not five?
Yeah, that's what I'm saying. It is also.
What is the interconnect between those groups? Why not do the same thing for one?
We are like combining it in the next step where.
But by the way, I mean the common column subset C.
Yeah.
Common column subset. It can C can span. Some elements of C will be in A, some can be in B. So what is this? When you do a loss A, M comma C, A minus A, CA is what? Columns of C in A, is it?
Yeah, like the column that we have taken, which will be that in A. For them.
I'm
So
not understanding why to what is two doing? I mean, CA finally you're reducing it to CA and CB. There's a
yeah,
CA, there's a CB. Then
yeah,
you find the loss, the
yeah.
best approximation, and I'm not seeing anything being gained by dividing into two. What happens in the next slide?
Let's go to next slide. So what we do here, we get both of these losses for A and B, and we try to see when the reconstruction error is getting maximized. It might be possible that for one of the group, the reconstruction error is very minimum, but at the same time, if there is much difference, for the other, it will be maximized. So we are getting maximum of them. And then we will form it as our, let's say, our Poisson
I
function.
mean, and is it just like saying, well, one of them might be a privileged, the other might have been non-privileged. So let me do well on the non-privileged. Right. Then I can have,
Something like that.
yeah, and you're saying you might as well have multiple instead of two, you have 10.
Yeah.
And you could just find ensure that the max across the 10 is minimized. But this can also lead to a potential problem that you're trying to just appease everyone and do suboptimally and all. Um, how do they solve the optimization problem, by the way?
Okay. Um, so they created approximation algorithm. Like for this, it is an NPR problem. So they try to solve it with an approximation problem. So they do it with one of them, trying to find, and then they did a subset of other which satisfies the whole thing. Which that algorithm is after that.
You'll present the algorithm,
Yeah.
right? Okay, go ahead.
So before that, they also consider a leverage store. So what does it do? It measures the importance of the columns which should be selected, which will be like capturing the top day structure of the matrix. So how is it defined? Um, so given the matrix M that we have, and we are getting a rank row that is data entry. Vitae, what is Vitae? So given this, when we will consider the cylinder vector, so top to right cylinder vector, that would be the Vitae. So for ith column, we are defining the leverage store. And here we, in this expression, Vitae I is not in the ith row of Vitae. Okay, sorry. So what is the idea behind leverage store? So we are trying to insert a threshold in here. So how is it done? So um, we insert a threshold that there should be at least $8 and some a tolerance within say epsilon is taken, which is between 0 and 1. So there is also a theorem defined. How is it done? So let's say we are going back to our standard problem. So there is a matrix M, and what we are doing, it's getting the same thing, and now we are inserting a model epsilon and making an interactive function with that. So what we are trying to do, such that our leverage store is greater than threshold for this, we we should have this expression valid. That is m minus ac plus m square. That's when 1/1 minus epsilon minus n square. So why do we do it? So it will guarantee relative error bound that is with respect to Rente approximation. If you go to next slide for pair subset selection, how does it work?
Sorry, what is the algorithm is still not clear. What is the algorithm?
No, this is just a major like which columns should be selected. It will like there are multiple columns and we want to select let's say only k columns. So which k columns should be selected? So whose leverage score is higher, we will select them. So this is for this only. Algorithm is
So it's just greedily based on leverage.
yeah, it is greedy based algorithm.
Given a matrix M and integer k, if as a subset of column indices that right there, LIM is greater than equal to theta cumulatively and C is a submatrix of M formed by the columns of S, then I see. So basically M minus CC selectional M minus the selected columns in M. Frobenius norm is less than equal to 1. So 1, okay, 1 upon 1 minus epsilon. Um, so they have got a 1 minus 1 upon epsilon approximation guarantee by Papilio-Paulus theorem, 2014. So they are leveraging. Okay, so this is just for the leverage scores. Okay.
Yeah. Next. So now trying to about fair cases problem. So there will be two leverage stores for both the matrix A and B, and both should be greater than the given threshold theta, such that the same can happen. Here we take the sum of both. That's why we have 1 minus epsilon for minus half, such that when we sum it comes to 1 minus epsilon. So and we take the sum. It's the sum that is, I mean, it should be at least theta. That should cross the threshold. Yeah, now coming to the algorithm, that is fair store sample. So yeah, as it is a dated algorithm. So what they do, it takes the leveraging store for both of them and take the tolerance of space. What they do, it initializes as high, as we know that leverage store should be greater than theta, but obviously it is now like high, so it should be um, low. So what we do, we take the maximum leverage store, like points, let's say alpha 1, beta 1 is maximum around them, and we add that to S. So what we do next, when we have that S, we try to find Q such that the threshold that we have is satisfied. It is a DDL, don't we are really selecting the maximum which is given the maximum threshold. Sorry, maximum um, leverage store. So that is how it's working. And in the finally we will just take union of both S and Q that we have found.
What is the other threshold? What is the other threshold? You're just greedily selecting. What are the threshold doing here?
Threshold is theta.
For what? Threshold is for what?
So like we are deciding the threshold that we can select the columns. So, like in the leverage store itself, we have decided a threshold such that we will select that much columns. How much columns should we select such that our threshold is reached. So we are deciding it can be tuned also. So like how much columns should we select such that its reconstruction is better. So in that term, we are designing a leverage store. So leverage store is being thresholded. Yeah. So now coming for the next matter, another concept is QR decomposition of any matrix. So how it works, we like decompose a matrix into an orthonormal and an upper triangular matrix. So that is here, and we also try a column pivoting where we get a permutation matrix phi such that it's like when we do QR decomposition of this, it will look like something this. So it can be like matrices R11, R12, R22 matrices, and the dimension of this can be as given in the slide. Then they present another thing that is rank heavy QR decomposition. So here they set a constraint that R11 will be large, R22 is small, and they try to find the rank of them based on that. Going ahead, they also went like low rank dividing QR decomposition and an algorithm for that also. So what is being done in here? So we are trying to compute pi t. So what is pi t? So it is also tolerance permutation, so that we can fairly select the tolerance also from both matrices A and B, and that in the low rank structure. So again, given the initial, we will initialize the QR factorizations A by A and QARA and QBRB, and we will perform the iterations for R22 and R1, R22A and R22B. So how we do that? We take the Claylin matrix. We take the Claylin matrices for both RA and RB, and we then select the maximum singular value. which we are getting for them. Then we perform the pivoting. We take it based on where we are getting the maximum cylinder value. Again, based on that, we perform QR decomposition. And when we are done with that, we update both our load permutation and global permutation. Yeah, then RA and RB are again updated, and this is iterated overall. So finally, we will have our tolerance of space. So this was another method that was proposed. Yeah. So now coming to the experiment, how is it performed? So the result papers. No, there are 2 papers and project proposal. Okay. So these are something that there are data sets and pre-processing steps that have been done. That are the value 114. That is very standard things. The results. Results should not be so. Yeah, the database is like here CSS is introduced here upon the classic CSS problem. So what is the advantage here that we can divide in the 2 groups, so we can make the bias reduce. We can reduce the bias that often happen while taking a single thing. So these things are done, and the paper shows the results that, but they show that it performs better. Even for the construction error, it might be slightly higher from the optimum value, but it even performs in terms of better in terms of fairness. For A and B, it would be balanced. So it also suggests the future word that we are also discussing, that we can get more than 2 groups. It says that, but it is not discussed in this paper. It is for future work. So, 2 papers and project proposal, but one was
First one was Gumbel SInkhorn.
okay.
Yeah, basically here, good. Yeah, the problem statement is we are going to perform the latent permutations in the deep learning, and normally these are used in sorting algorithms and jigsaw puzzles. These things. Basically, we are going to take a discrete data and make it into a differentiable function, and then use gradient descent. Yeah, this paper contributes like it says SInkhorn operator, which uses softmax theorem like thing, and then SInkhorn, it proposes SInkhorn networks and Gumbel SInkhorn distribution. Yeah, this is SInkhorn operator. We obtain it by first exponent means e power x. Then we normalize it, row normalization, column normalization, and limit L is L tends to infinity. Means L we keep a specific large numbers. And this is SInkhorn networks. Basically, we are not using this much.
Yeah, why is there no Frobenius norm here?
Didn't hear.
know about Frobenius law?
Mm.
Yeah, yourself into Frobenius law. What is the Frobenius law?
In Frobenius norms, we just actually calculate the mainly the sum of square error. So there we are minimizing that.
This is also the Frobenius law.
Yeah. We are also here also we are minimizing that. Here it is a bit different because there we are squaring and then taking a square root of the sum, and here we are not doing that.
Here it's still Frobenius law, but of the why is it this? What is the standard? Why is this the option? Why would you like x to be equal to beta and x hat equals? Why would you like each excite? I mean, the point is why do you like each excite to be the permutation applied to excite? Exactly what it is I column or is I excite. What is excite here? The notation, what do you mean by excite?
No, I don't know, bro.
You're not able to recall?
Yeah.
See, just because some other team presented doesn't mean you skip over it, no? Yeah, have you not prepared?
Yeah,
Sorry?
we haven't prepared this much.
No, just because some other team presented doesn't mean you don't prepare, no? That's not acceptable. So you don't know what is XI, right? You don't know what it's doing exactly.
Based on these, I've not gone through this paper, his paper. So basically, maybe it's an input pair. Xi is an input pair we are providing to the model, and x bar is predicted value so that we are reconstructing from the model.
So you're saying XI is an ith instance. It's not it's not ith column of X.
Yeah, I don't think so. It's a column.
It doesn't look like. I mean. Can you just go back? What notation? Go back. Yeah, one slide before that. I mean, somewhere they were.
Here in the definition of the Synkron
What is
operator.
M? What is M? I want to see what is M.
N.
M.
M.
I think M is the number of columns. MX. They have written MX here, right?
X is the input matrix, and M is just basically maybe the operator which is collecting the major chunk of the matrix which is performing higher towards the model, like which has higher connectivity with the results. What is actually happening in case of X,
How is temperature?
So what is the theorem on X of X? What is it actually? What is the second term? H of T is
What it is?
H of T is written there. It's aircraft.
H of
What is the first term? Gone back deeper into this.
Yeah. Okay. So, I mean, you're going to be penalized, right? So, should I penalize the group or penalize an individual? So, I mean, you have got sufficient time, right? And just because another team presents, you are
yeah,
exempt.
we changed the paper yesterday. Like
Sorry?
we changed the paper we were presenting yesterday
Yesterday.
because we selected other papers, but yeah, they said we can't select from some random conferences.
So the other two papers you changed only this paper yesterday, is it?
Yeah,
The other two papers you seem to have prepared long back.
yeah. Yeah, but we selected a different paper, means outside paper. Yeah, that was Gumbel SInkhorn IPF.
Actually, Gumbel SInkhorn is a very fundamental thing for your post project also, right? And from the project perspective, at least, understanding is important. You can't say you change the paper you're presenting, but Gumbel SInkhorn was supposed to be something you should have understood, right? Okay. Just run through the slides. What is it? So you're not prepared, so you can just read it. That's I see. So M is not clear to you. Fine. Next. Yeah. So network must behave consistently at input permutations. Next. So you're seeing rank one perturbations. Okay. Okay. Next. So yeah, Gumbel matching is not differentiable. So relaxing SInkhorn operator, which produces doubly stochastic matrices. Next. That team is not here. We represented Gumbel. Next. Okay. Variational inference of Gumbel SInkhorn. Yeah. Next. So these are experiments. Fine. You can skip this. Go to your project description.
Yeah, currently models are based. Currently, permutation-based models are mainly static, means, and static means they're ignoring training dynamics, and is unfair, means we are using that fair CSS for that, and it's inefficient for large-scale training models. So we are going to select easier to and difficult, means we are going to separate easier and difficult samples using the Gumbel SInkhorn and make the model difficulty aware using a loss function. Means we will make a loss. We will use a curriculum driven loss function, and if the loss is less, means we will consider it as a easier, and yeah. Hmm? Yeah. Yeah. Yeah, using Gumbel SInkhorn, we are means we will get a doubly stochastic matrix, and then we will use a loss function, and we will find the losses for it, and it means in the training data, and for the less loss we will consider it as easy, and with higher loss we will consider it as difficult data. Read. Yeah, CSS, that paper means, yeah.
So this you seem to be a little all over the place, right? I mean, curriculum aware, permutation selection. Yeah, house curriculum driven laws that aligns model training with sample difficulty. Fine, that by itself is okay. How is it related to the permutation? You think integrate a Gumbel SInkhorn model to produce differentiable permutation matrices to prioritize easy. So you're saying you want to use permutations or column selection, subset selection to help curriculum.
Reduce that everything there.
I'm not even able to connect the dots here. Group fairness wise. I mean, you're not able to defend your bullet point. You can be asked, did you just LLM to generate? Because I'm not able to connect these points. Right? Second is group fairness by soft constraints built on techniques like fair CSS to encourage fair representation of different data groups. Fine, that by itself is an area. Underrepresented, high variances suddenly come in there. Equitable subset formation. Okay, so this, I don't think you have written points. Project proposal. I mean, see, now you can't say paper change, the project proposal. Project proposal is supposed to have been ready long back, right? I mean, you don't have time now. The idea is use these presentations to dive deeper. You have to take, I mean,
Basically thinking of integrating these 3 papers and
integrating 3 papers, how can it be one project?
Not-
A project,
not
you
integrating it.
can't just integrate paper and create a project. You need a project description, right? What is your project problem? Then you can see how each of these papers can play some role. Like some of the other people, other students found some strengths from one paper, some strengths from another paper, combine them, that is fine. But you're not identified even what strength you will get from each of those papers. You say combine the 3 papers and what merit from each paper. Hey, you'll have to take your project very seriously. Huh? This cannot work. You yourself be lost. Okay. So please talk to Pratik once and but rework it. Would you suggest something?
Yeah, I think so. Since you brought up curriculum, this setup, I think. So you can try this. In terms of your post project as this. So you have your batch wise training samples that you're selecting samples from that batch. Does that using Gumbel SInkhorn, because your batches are matrix also. You are selecting permutation matrices over that with some samples. On that sample, you get this.
Are you saying using Gumbel SInkhorn for data mixing?
No, data mix, not data mix, substation similar to grad match and all. Although we are not using gradient information, but this features.
So not really don't work with transformers. Not exactly.
Not in that.
Just Gumbel SInkhorn for subject selection. That sounds doable, but
Normal technique. Quest classification.
okay.
So the relevant data type. So the same pattern you have to just get for external prediction.
Yeah, so if you can write this down and share with you. Okay, is this clear? Focus on curriculum, SInkhorn curriculum. Let's not go into any of the other areas. This is, I think, what seems to be the solution. Okay, thanks. Anyone else?